Under condensation methods, I think we are done with chemical methods. We'll have to continue with the physical methods. So under condensation methods, we are now doing the B part, which is physical methods. So these physical methods are used to prepare the colloidal solutions. One is by exchange of solvent. So what happens here? When we have a true solution, and this is mixed with an excess of other solvent. When a true solution is mixed with an excess of other solvent in which the solute is insoluble but miscible, but the solvent is miscible. In that case, a colloidal solution is obtained. A colloidal solution is obtained. What is an example? Example is, for you have a solution of sulfur in alcohol. When a solution of sulfur in alcohol is poured in excess of water, a colloidal solution of sulfur is obtained. Example 2. When a solution of phenolphthalein in alcohol is poured in excess of water, a white solution of phenolphthalein is found. Is by exchange of solvent. Means initially there was one solvent and now we are going to change the solvent. And the resultant would be a colloid or a colloidal solution. So, can I clear the screen? So, I'm clearing it. Next, we have excessive cooling. The second physical method under condensation is excessive cooling. So what happens now? Molecules of all these substances, some substances, they condense together when we subject it to excessive cooling. So what happens? Molecules of certain substances condense together on excess cooling to form colloidal size particle. So the colloidal solution of ice in an organic solvent such as chloroform or ether can be obtained by freezing a solution of water in the solvent. So what happens? The molecules of water which can no longer be held in solution separately, they combine to form particles of colloidal size. Next is by condensing vapors of a substance into solvent. So what happens? Example, substances like sulfur and mercury in water are prepared by passing their vapors in cold water containing stabilizing agents like ammonium nitrate in small amounts. Okay, so excessive cooling is the second physical method. By condensing vapors of substance into solvent is the third physical method under the condensation methods. I am clearing the screen. If anyone wants me to go back, I can, or we can wait. Next, we have dispersion methods. So dispersion methods means large particles of substances are first broken into particles of colloidal dimensions. Colloidal dimensions in the presence of dispersion medium. In the presence of dispersion medium. What happens first? Some substances are there and those substances are broken into particles in which the dimensions are like a colloidal particle in the dispersion medium, and this colloidal things are stabilized by adding stabilizers. So what are the methods? First is mechanical dispersion. Mechanical dispersion. So here this happens in a colloidal mill. First, what happens? First step. Substance, whichever is there, is finely powdered. Second, it is shaken with you put it in the dispersion medium and shake it to form a suspension. Next, the suspension is passed through the colloidal mill. Next, the simplest type of colloidal mill is disc mill. I'll tell you how it looks like, which consists of two metal discs nearly touching each other, but they rotate in the opposite directions. And rotating in opposite directions. Next, the direction at a high speed, that is 7,000 revolutions per minute. Now, the suspended particles are broken to produce colloidal sized particles. This method is used specifically for preparing ink. So what happens first, you just try to powder it by passing it through the mill, shake it in the presence of dispersion medium. The suspension, whatever is found, is again passed through the colloidal mill, where you have two discs, one opposite to each other, and they rotate in the opposite direction. In between, we have the colloidal solution, and that is all broken down into the exactly size of a colloid. And then you have the final solution. We use it for mainly preparing ink. The next way of dispersion method would be electrical disintegration, which is Briggs arc method. It's important. I hope you copied this. I'm clearing it. I'm clearing it. Next, we have electrical disintegration of Briggs arc method. So here we have electrodes. This is ice bath. This is H2O plus KOH, more like stabilizer. This is dispersion medium. So this process involves dispersion as well as condensation together. This involves dispersion and condensation. So, colloidal salts of less reactive metals such as gold, silver, platinum, copper, lead, etc. can be prepared by this method. So what happens here? First of all, electric arc is struck between the electrodes of the metal which are immersed in the dispersion medium. So what happens? The intense heat produced, it is going to vaporize the metal, which again then condenses because it has the ice now in the bottom, which then condenses to form particles of colloidal size by the ice. Here KOH is the stabilizer. KOH is the stabilizer. Please copy. Next we have two more methods. Ultrasonic dispersion. Ultrasonic vibrations, you generally know, they have high frequencies. So, ultrasonic vibrations can bring about the transformation of coarse suspension or liquids like oil, mercury, etc. into colloidal range. So this is used for preparation of metal oxides and metal sulfide salts from their suspension. Peptization is nothing but, digestion of proteins by peptin, which is an enzyme called pepsin. What is this? This is a process of converting a precipitate into colloidal solution by shaking it with the dispersion medium in presence of electrolyte. So whatever electrolyte which you are using here is nothing but the peptizing agent. So this method is specifically used to convert a freshly prepared precipitate into colloidal solution. So this method is generally applied to convert already. So what happens during peptization? During peptization, the precipitate absorbs one of the ions of electrolyte on its surface. The ion adsorbed on the surface is either cation or anion of electrolyte. This causes the development of charge, of positive or negative charge on the precipitates, which ultimately break up into particles of colloidal range, colloidal dimension. I'm clear in this. We'll look at an example. So we specifically use this for freshly prepared precipitates. So when freshly prepared FeOH thrice is shaken with aqueous solution of this, which is acting as the agent. So this is going to absorb Fe+3 ions and break further into small sized particles. FeCl3 is Fe+3 plus 3Cl minus. So FeOH thrice is reacting with the Fe+3 ion, becomes FeOH thrice and the Fe+3. Example. So many others are there. Freshly prepared AgCl can be converted into a colloid by adding HCl. We have AgCl and Cl minus colloid. Third, cadmium sulfide. Cadmium sulfide can be peptized with hydrogen sulfide and you get CDS S-2 as the colloid. Okay. Next, we have purification of colloidal solutions. Only two methods. Some properties of colloids. Electrical properties. So much. By Saturday, we'll be able to complete the chapter. So much of theory, I know. Purification of colloidal salts. So colloidal solutions, you know, they are obtained by various methods and most of them are impure. So they have impurities of electrolytes or other soluble substances and all. So these can actually destabilize the solution. So we have to remove them. So a very important method is dialysis. What is this? We actually remove a dissolved substance from a colloidal solution by means of diffusion through a suitable semi-permeable or whatever membrane. Because particles in true solutions can easily pass through any membrane or parchment paper or cellophane sheet and all. But you know, colloidal particles cannot pass through them. So we use a dialyzer. We use an apparatus called dialyzer. So we have a bag of suitable membrane. It contains the colloidal solution. We have, what is the process? This is the impure solution. Impure solution. These are the electrolytes. We are passing distilled water. This is the cellophane bag. What happens here? You can see a bag of suitable membrane. With the colloidal solution is suspended in a vessel through which fresh water continuously flows. What happens? The molecules and ions, they diffuse through the membrane into the pure colloidal solution left behind in this. So the movement of ions across the membrane can be expedited by applying electrical potential. Through electrodes. So this is through electricity, it is quicker than a basic dialysis. We have the second method. So what do we use this method for? Dialysis, you know, na, purification of blood in kidney. An artificial kidney machine. Next, we have second method called ultrafiltration. That is the second method of purification. We have ultrafiltration. Here, colloidal solutions are purified by carrying out filtration through what will these do? Allow only electrolytes to pass through. These filter papers, they have a particular pore size. By impregnating with the colloidal solution, means matching with the colloidal solution, and subsequently they are hardened by soaking in formaldehyde. That's all. We are done with the purification. Okay. Properties of colloidal solution. See, so colloidal solutions are heterogeneous in character and they have two phases that we know. One is dispersed phase, the other one is dispersed medium. If you look at the visibility, because of the scattering caused by the colloidal particles, it will actually appear as a bright spot moving randomly. If you look at them. Scattering, due to scattering caused by the colloidal particles, it will appear as a bright spot, whatever particles are there. Colloidal particles, these are like, if you want to write anything, you can write down from what I say. Colloidal particles, they pass through any ordinary filter paper. That means the particles do not pass through the other fine membranes, but through normal papers, they pass through. Colloidal solutions, they have colligative properties, that is relating lowering of vapor pressure, elevation and boiling point, depression and freezing point, and osmotic pressure that you might have learned in solutions. However, due to average molecular masses of these particles, mole fraction of dispersed phase is low. And these colligative properties, whatever you observe, are very small. So colligative properties are being showed, that's all. Filter, how are they filtering? We discussed. Tyndall effect. Tyndall effect also we know. Tyndall observed that if a strong beam of light is passed through a colloidal solution, which is placed in a dark place, the path of beam gets illuminated. That's called Tyndall effect, because of scattering of light by the colloidal particles which are present in the solution. So this phenomenon, due to scattering of light from surface of colloidal particles, you know that this is not possible in a true solution nor suspension properly. Next we have, what are examples of Tyndall effect? You know the blue color of sky and sea water. It's because of the reflection. Light thrown from a projector in cinema hall. Okay, and this Tyndall effect is used in making microscopes and finding whether a solution is heterogeneous or homogeneous. And some mechanical properties, if we have to know, one is the Brownian moment, which you might have learned in 9th standard also. Brownian moment is that random motion, like pollen grains randomly moving in water, or when you have a dark room, suddenly you pass sunlight through it, you see dust particles randomly, continuously moving. Right. So this phenomenon was observed in the case of colloidal particles. When you see them in ultra microscope, the zigzag motion of these particles is called the Brownian moment. Okay. So we know the dispersion medium is there and the colloidal particles are randomly moving. We call this movement zigzag moment, random moment, continuous moment as Brownian moment. So in the Brownian movement, you understood what it is. I'm not writing what is Brownian movement, but what all we have to learn or write is one. Size of colloidal particles according to this is about the dependence. Size of colloidal particles, the mobility, movement is inversely proportional to size of the particles. Viscosity of solution, mobility, viscosity, temperature, mobility, so factors affecting Brownian moment. If particles, I already wrote no. What happens? If particles are large, Brownian moment is less. If temperature is more, Brownian moment is more. Brownian moment, it does not change with the time. It remains same for a long time. That's all. This is about the Brownian moment. So I'm clearing it. Next, we have electrical property. If you have any charge on these colloidal particles, then that is confirmed by an experiment called electrophoresis. So when you have two platinum electrodes, they are dipped in the colloidal solution like we have seen before. The colloidal particles will move to some one part of electrode depending on the charge they have. So this movement of applied movement of these colloidal particles under this applied electrical potential is only called as electrophoresis. It's very easy. I just want you to write electrophoresis. It helps in finding out the existence of the charge on colloidal particles. So when you have two platinum rods like this, one platinum rod, one platinum rod. This is the As2S3 solution, which is negatively charged. Then what happens? So if you, when the electricity is passed, electric potential is applied. Then the colloidal particles move towards one electrode. We know that the positively charged particles move towards the cathode, negatively charged anode, depending on direction of moment. Depending on the direction of moment, you call it as anaphoresis if at all it is going towards anode. It is called as cataphoresis if at all it is going towards the cathode. Example, arsenious sulfide. Like how I wrote on the top, arsenious sulfide is what I wrote. Gold, silver, and platinum particles, these are negatively charged. While iron hydroxide, aluminium hydroxide, these are positively charged. So I'm clearing it. We have so many terms here. Electroosmosis, sedimentation potential or Dawn potential, isoelectric point, steaming potential. These are the last 4 things that we are learning today, and I'll be ending the session. Yeah, I'm sorry, Adhyasha. Okay, sorry. Whoever has copied this can leave. We are done with the class. Whoever has completed copying can leave. Thank you and good night.